8, talking about p-values. So just like before, we're going to compare one thing against another to determine whether or not we reject the null hypothesis or fail to reject the null hypothesis. In terms of the critical value, we drew a threshold and we needed to compare our sample mean in standard error units. So that means actually our t-score. We compare our t-score to our critical value, and we use that to determine whether or not we should reject or fail to reject the null hypothesis. In terms of p-values, we do the same kind of thing. We're going to have a threshold, and that threshold is our significance level. So remember, we have our confidence level in here, and the significance level is the probability that's left. So we'll compare that probability that's left, that as a threshold, to the p-value that comes from our data. And if the p-value is less than the significance level, then we will reject the null hypothesis. We will say effectively the probability is so small to see what we saw given the null hypothesis that the null hypothesis is probably not true. So we will reject the null hypothesis. Conversely, if our p-value is large, then we will say, yes, it is likely enough to see what we saw under the assumption of the null hypothesis that we're okay with the null hypothesis. We will not reject it. Now, again, it doesn't mean that the hypothesis or that the value we are hypothesizing is correct. The population mean might not be 211, but our results are consistent with the hypothesis that the mean is 211. So that's good enough. So that's ultimately what we're going to do. Compare the p-value that we get from our data to the significance level that we set ahead of time from alpha. And here's the formula that we are going to use to do that. We have a t here because we're dealing still with a t distribution. The dot dist formally refers to the distribution. At least that's what Excel thinks it means. I think it works better to think of that as distance. So we are going to give Excel a distance away from the mean in standard error units, and it will give us a p-value. That's why we use the dist and not the inverse. Because we are doing a one-sided test and we are interested in the right-hand tail, remember we had a rejection region that was over here, and we also add the .rt. And so that's what we put in. So the number here is not the critical value. The critical value is over here referring to our rejection region. We want to know how far away our data are because we're dealing with the probability of seeing our sample mean. So we need to know how far away our sample mean is. That negative sign becomes very important. That tells us our sample mean is off to the left. And it's off to the left, minus 5.5 standard errors. So we put in minus 5.5 standard errors. We also put in our degrees of freedom, number of data minus 1. And Excel tells us that there is a 0.98 or a 98% chance of seeing a value as extreme as we did or something more extreme. And more extreme means off to the right. Simply put, that p-value, 0.98, is substantially larger than our significance level of 0.1. Since 0.98 is greater than 0.1, we also fail to reject the null hypothesis. That's good because we also failed to reject it from the critical value. Critical value is over here. Even though we have a big number, we did not cross the critical value into the rejection region, so we failed to reject it. We're saying, wow, it is really likely to have seen the result we did or something more significant. So all of that area of the curve. And that is why this number is so big. So the total area under the curve has to equal to 1. The area from our sample mean to the right is not 1, but it's really close to 1. So it should include most of the area, and in fact it does. So that's kind of our double check that yes, the p-value makes sense. We were way off to the left, so we should be including almost all of the area to the right of the curve. Should be close to 1, and it is close to 1. So hey, go us. The last part here, and we'll just add this in, uses the confidence interval. Now we can calculate a confidence interval, um, and that tells us, again, it gives us the range in between critical values, so a negative critical value and a positive critical value. It gives us this range, but in original data units. So critical value is in number of standard errors from the mean, and the confidence interval is in the original units. So it has to match that 211 and that 167. It's actually in megatons CO2 per year. However, as we can see here, the confidence interval is always based on a two-sided test. Our hypothesis test, the one that we did to reject or fail to reject the null hypothesis, is a one-sided test. So yes, we can calculate a confidence interval, but because the confidence interval is a two-sided test, and because of that we get the same thing that we do for question number 7, because the confidence interval is a two-sided test, and our hypothesis test that we're doing is a one-sided test, we cannot use the result of the confidence interval to compare or to reject or fail to reject our null hypothesis. We can only do that if our actual hypothesis test was two-tailed, and it was not, so we can effectively skip that part.